Hello everyone, I am Fivel from Ben-Gurion University, together with Dr. Moshe Klein and Professor Maimon from Tel Aviv University. We'll present our paper, Decision Trees with Soft Numbers. Nowadays, there is a challenge to describe the special reality that a person lives in two worlds, the real world and the virtual world. For example, metaverse, a new technology that incorporates a virtual reality in 3 dimensions with internet connection and generates a virtual experience to the user. In the CSL lab in Tel Aviv University, a new mathematical language was developed by Dr. Moshe Klein and Professor Maimon. That is called soft logic, that involves multiples of zero. I'll explain its principle in this presentation. That language may provide an answer to the question how to realize the new world created by the metaverse. Long story short, after I heard about soft logic and soft numbers, I came with an idea, together with Klein and Maimon, to implement the soft logic into probability theory to develop a soft probability of events which would have a zero probability in the classical probability theory. We believe that soft probability together with soft logic will help us to understand the new world created by the metaverse. Now we provide some abstract of our paper. In the classical probability theory, for continuous random variables, we cannot distinguish between probability involving strict inequality and non-strict inequality, because probability involving equality collapses to zero. In our work, we use soft numbers that added a new axis contains multiples of zero to present soft probability that will create a distinction above by generating soft zero multiples of a PDF. We also extend the soft probability notion to other classical definitions like unions, intersection, expectation, entropy, etc. We found potentially another soft axis, multiples of 0 log 0, due to soft entropy. We also extend the soft entropy notion to cross entropy, KLD, there 0 log 0 is vanished, and to mutual information that can be used for splitting criteria in decision trees with data set of continuous random variables consist of single samples and intervals. Here are the following topics for the presentation. First, I present the introduction of the problem with a brief reminder of probability theory. Then I present our motivation for our work and the main idea for our approach. I provide an overview of soft logic that assists us to define soft probability. I will show some examples and extension for other classical terms like union, intersection, expectation, entropy, etc. Last extension will be soft mutual information as an application for decision trees. I'll end this presentation with conclusion, summary, and suggestion for future research. Suppose capital X is continuous random variable, or CRV. We know that we cannot distinguish between a probability of X to be less or equal to little x and X to be strictly less than X because probability of X equals X collapses to zero. Well, in some sense, we lost some information because the event X equals X is possible, but still has zero probability. It's a fact that we can approximate the probability of capital X to be adjacent little x up to a small delta x based on X PDF. Despite that, our motivation is to distinguish between strict inequality and non-strict inequality probabilities of CRV, and to assign some value for PR of X equals X that will not collapse absolutely to zero, so we can obtain some information for it. Inspired by these two trivial equations here, our approach is to implement soft numbers. So each zero probability object, P of x equals x, is on the zero axis equals to the PDF fx of little x that achieves distinction between strict inequality and non-strict inequality probabilities. Our conjecture is the soft numbers will improve the performance of decision trees because we can obtain some additional information by the above distinction regarding to the probability calculation that will make more accurate decisions. Here are outlined some basic definitions and axioms of soft logic developed by Klein and Maimon. 1 bar presents multiples of 1, the familiar real axis, and 0 bar multiples of 0. And absolute 0 is 0 times 0 bar. These are the axioms of distinction and ordering among 0 bars multiples, addition of 0 bars multiples, and nullity, product of two 0 bars collapse to 0. Axiom 4 defines bridging operator, an addition of 0 bar element and 1 bar element with two types. Left type is A0 bar, bridge 1 bar, and the right type, B1 bar, bridge A0 bar. Axiom 5 says that the bridging operator does not commute. In other words, the left type, namely 0 plus 1, and the right type, namely 1 plus 0, are not the same. A soft number is defined to be the set of two types of its associated bridge numbers, the right type and the left type. Here I show the development of the soft logic coordinate system. Instead of drawing a standard horizontal number real line, we have horizontal line presents 0, 1 segment and vertical 1, infinity segment. With this, we have geometric representation of the mapping f equals 1 over x. It can be shown that all the diagonal lines that connect 1 over x in the vertical line to x in the horizontal line intersect at one point, 1 unit below the 0 plus point. After continuing the drawing antisymmetrically, we have created a vertical line through the 0 plus point with 2 units length. The midpoint will denote the absolute 0, and below that, 0 minus. That line is extended here and present the 0 axis. We complete the soft logic coordinate system as a mirror along this 0 axis, but with negated signs. Each soft number, x0 plus y, is a set of 2 points, C in the front and C prime hidden behind this page. Each soft number is expressed by assigned height A and width B between 0 and 1. Relation between xy and AB is obtained by equating coefficients of 0 bar term and real term. Operations that can be done on bridge numbers are addition and subtraction by collecting like terms, multiples of 0 and 1. Multiplication and natural power based on nullity axiom. Product of two 0 bar terms collapse to 0. Natural power results derivative power rule in the 0th part. Therefore, we define polynomial and function on bridge numbers input A0 bridge x as the following soft number output. The output soft part is a 0 bar coefficient in the input A times the function's derivative at the input real part x, and the output's real part is the function itself at the input's real part x. We have a CDF at the bridge number accordingly, with the PDF in the 0th part. We extend this notion to the soft numbers so that each operation contains the two types of the bridge numbers by replacing the bridging operator, that is, the perpendicular symbol, by the dot plus symbol. Suppose capital X is a continuous random variable. We define a soft probability function denoted by PS by the following. PS of capital X is less than or equal to little x is defined to be a CDF of capital X at a soft number 1 times 0 bar dot plus x, resulting a regular CDF in the real part and PDF in the soft part. We can decompose the event capital X is less or equal to little x into disjoint events. Capital X equals little x, union capital X is less than x, so that the soft probability of capital X is equal to little x corresponds to the soft part, the PDF, and the soft probability of capital X is less than x correspond to the real part, the CDF in the regular sense. With this definition, we obtain the distinction between non-strict inequality and strict inequality probabilities. And also, we have interpretation of probability of equality that does not collapse absolutely to zero. We illustrate the soft probability with the following examples: Gaussian and uniform distributions. When capital X is Gaussian distributed with mean mu and variance sigma square, the soft probability PS of capital X equals little x is this Gaussian function times 0 bar. If and only if little x is closer to the mean than little y, then we obtain a higher soft probability at x than y, which makes sense, but both of them collapse to zero in the regular sense of probability. Since the support of the Gaussian capital X is infinite, we have a positive soft probability for any little x and y. When capital X is uniformly distributed on the segment A, B, the soft probability is the reciprocal of the segment length B minus A times this indication function denoted by this one symbol times 0 bar. For all x in the support, the segment A, B, and for all y outside of the support, we have a uniform soft probability of x that is positive and thus possible, and higher than in y, which is completely zero, namely impossible, because it's outside of the support. For summary, thanks for the soft probability, we can distinguish among events that would collapse to zero in the regular probability sense. Now we outline some results for soft probabilities on complement, union, intersection, and conditional probability. We start with equality types. To calculate PS is not equal to X, we need to use the complement to X is not equal to X. That is X equals X. So we have PS of X is not equal to X equals a negative PDF at X times 0 bar plus 1. Soft probability of union of X equals Xi for distinct Xi's equals to the sum of the PDF at Xi's times 0 bar. The intersection, however, is an absolute zeros if some of the Xi's are distinct and is soft zero Fxi if for all Xi are the same. Similar result is obtained for the conditional soft probability PS of X equals X given X equals Y. Here we outline union, intersection, and conditional soft probability regarding to X is equal to little x and X in the open interval A, B. For that union, we have in the real part the CDF difference that we are familiar with in the classical probability, and in the soft part, the PDF at little x types indicator of little x is outside of the open interval A, B. If little x is in the open interval A, B, then the probability will be redundant to be x in the open interval A, B. And we have only the real part in the right-hand side result. For that intersection, we have a soft zero PDF of x at little x times indicator of little x in the open interval a comma b. If little x is outside of the open interval a comma b, then the soft probability will collapse to 0. Conditional soft probability of x is equal to little x given capital X in the open interval a comma b is obtained by the Kolmogorov definition and also by Bayes' theorem to have a soft zero in the right-hand side. These notions are extended to the non-strict inequality cases, and the changes are shown in blue, so that we evaluate the indicator of the single point is in or outside of the closed interval a comma b accordingly. In the union, the sum fx of a plus fx of b is added to the soft part by decomposing the non-strict inequality into disjoint equality and strict inequality accordingly. Now we extend the notion of soft probability for two continuous random variables, capital X and Y. First, we decompose the soft probability on the left-hand side involving non-strict inequalities into a sum of soft probability terms that are disjoint. Then we define the following equations that determine the terms in the right-hand side of the top equation. Whenever we have equality such as in the first two sub-bullets, we define a soft probability involving CDF partial derivative. Whenever we have strict inequality in the last bullet, we define it as the CDF itself, such as in the regular probability. Combining the soft probability terms above, and we have this soft number that has the CDF in the real part and the sum of partial derivative in the soft zero part. Similarly, we can derive soft probability of events intersecting non-strict inequality and strict inequality of different variables, and also of events intersecting non-strict inequalities and equalities of different variables, where in the last case, we have the soft zero. In this slide, we define the soft expectation. For this, we assume that a continuous random variable, capital X, is distributed according to a PDF fx. But we also assume that X is within a set of the disjoint open interval aj, bj, and single points xi, denoted this by this script capital X. We define the soft expectation denoted with ES as the sum of soft probabilities weighted with a single point xi's plus the sum of the integrals of xfx integrand within each open interval aj, bj. The result is a soft number denoted with a soft part ni x and real part kappa x. A soft expectation of a function g applied on x, where g maps from R to R or to the soft numbers, is defined similarly by the following soft number. For instance, we can define a soft variance based on this definition as follows. We define a soft variance by Vs as a soft expectation of square of x minus its soft expectation. After some algebraic manipulations, we have a soft number with the real part a non-negative number lambda x squared and a soft part gamma x that might be negative. We have defined a soft entropy denoted by Hs by the following. Similarly, how entropy is defined in the regular sense. Here, the basis of log is arbitrary. The sum in the right term is a real number that looks similar to the differential entropy of a continuous random variable, while the sum in the left term that looks similar to the entropy of a discrete random variable is decomposed according to the logarithm rules to generate two sums. Multiples of 0 bar log 0 bar in the left and multiples of 0 bar in the middle. The object 0 bar log 0 bar, we defined it to be a new type of soft zero denoted by 0 double bar. If we combine the soft zero in the middle with the real term on the right and factor in a negative sign, we obtain a negative soft expectation of a log composed with the PDF fx of x, which might be a simplified version of a soft differential entropy. However, we might not discover this possible of a new soft zero with the form 0 log 0. We define a soft cost entropy similarly to a soft entropy, but composing log with another PDF, fx hat. We defined a soft KLD denoted by ds as a difference between a soft cost entropy and soft entropy. The 0 log 0 term of a soft cost entropy is identical to the 0 log 0 term in the soft entropy. So the subtraction cancels out this term, and we're left with this soft number shown in the middle that can be written as a soft expectation of a log of fx over fx hat. We use this notion of a soft KLD for a soft mutual information as a splitting criteria in the decision trees. Decision trees like ID3, C45, etc. are simple yet successful techniques for predicting and explaining the relationship between some measurements about an item and its target value. In most decision trees, splitting criteria is univariate, namely internal node is split according to a value of a single attribute. A splitting criteria of a features X and label Y under cost function expectation C has the following structure: C at Y minus C at Y given X. If the cost function is the entropy, then the splitting criteria is the mutual information I of Y semicolon X. Consider the two random variables X and Y conditioned to be in the set script X and script Y respectively. We define a soft mutual information of Y and X denoted by IS as a soft KLD of the joint PDF fxy and their product fx times fy. The soft mutual information is a soft number involving a double sum over all xi's and yj's in the soft part, and a double sum of a double integral over each open rectangular domain AI, BI, cross capital AJ, BJ in the real part. The representation in the middle is symmetric between X and Y. The representation in the end is equivalent, by Bayes' rule, but less symmetric. It emphasizes the splitting criteria structure that subtract the cost function of Y given X from a cost function of Y. Here we demonstrate a simple numerical example for a computation of a soft mutual information, IS, with X and Y are jointly Gaussian distributed, and each of them may have a single value, X0 and Y0 respectively, or it's an element in a single interval, little a and b and capital A and B respectively. We ran simulations of different cases. We can observe that when the intervals are located far away from their related mean, for example, A and B is 2030, the real part of the soft mutual information, IS, is much lower, 10 to the negative 87, than those that are adjacent to the mean. And likewise, when X0 and Y0 are far away from the mean, we have a low value at the soft zero part. To summarize this presentation, in the classical probability, in the continuous random variables, there is no distinction between probability involving strict inequality and non-strict inequality, so that probability involving equality collapses to zero. Soft numbers assist us to distinguish between the probability involving strict inequality and non-strict inequality, and among the discrete values for CRV by generating soft zero multiples of the PDF observations. We extended the notion of soft probability to classical definitions from probability and information theory, like unions, intersections, expectations, entropy, mutual information, and so on, where soft mutual information is applicable for splitting criteria for decision trees. And we also discover a new soft zero object with the form 0 bar log 0 bar. For future research, we suggest the following: to extend and explore the notion of soft probability for continuous random vector and mixed random variables that have a continuous PDF and non-zero probability in countable points. We suggest to investigate the consequences of negative soft part variance and for 0 bar log 0 bar and possible application for those. Finally, to implement soft probability into more technological topics like in information theory, data mining, machine learning, computability, cyber physical system, metaverse technology, and so on. This paper was supported by the Foundation Grant for Smart Cities and Digital Living 2030 bestowed upon the universities of Stanford and Tel Aviv. We're happy to express our thankfulness and gratitude for this support. Here are some references for the paper. Thank you very much.